Professor, can you hear me?
Yeah, good morning, Ivan. Can you hear me okay?
Yep.
Perfect. All right, let's get started then. Hello, good morning, everybody. Nice to see you all. Welcome to everybody in Marcus and everybody on the live stream. I hope you guys are having a good week so far. So this week we are finishing up chapter 2 today. And then on Thursday, we'll start chapter 3. And we have our chapter 2 quiz on Friday. So as a reminder, at some point on Friday, you need to find a 1-hour period, log into Moodle and take the chapter 2 quiz. It's exactly the same in structure as the chapter 1 quiz. So 10 questions, multiple choice. And there is a review for the chapter 2 review that's posted on Moodle on Thursday night. I sent an email about that with the Zoom link as well as the time. So today we're going to be doing 2.4, which is the second derivative. So this is sort of an extension of 2.2, the derivative function. And we're also going to do 2.5, which is marginal analysis, which just is an extension of our cost and revenue stuff that we did in chapter 1. So hopefully we'll get through everything, but if we don't get through sort of the last example in 2.5, you can always watch that example on the asynchronous videos on Moodle if we don't get through the last example, depending on how long everything else takes. So we're just going to get rolling now. I'm going to switch over to the doc cam. Okay. So last week you watched videos on the derivative function and explored the relationship between the original function and the first derivative. And so we sort of alluded to the fact that the second derivative might be something that is of importance to us at some point. And so today we're going to talk about what the second derivative is, why we'd want to use it, and how we can figure out properties of the second derivative that will be relevant to us. Okay, so when we take the derivative of the derivative, that is called the second derivative of the function. Okay, and the idea is that if we do the same type of analysis on the first derivative that we did on an original function to go to the first derivative, that will help us bridge from the first derivative to the second derivative. And I will mention, you can take third derivatives, fourth derivatives, fifth derivatives mathematically, but they really start to lose their meaning after the second derivative. The third derivative does have some applications in physics, but after that, the derivatives that are higher order, is what we call them, are really used for pretty advanced and complex mathematics. So unless you're going on to take, graduate level mathematics, the fourth derivative and so on won't be applicable. In this class, we only study the first and second derivative, but just know that you can apply the same type of logic to talk about other derivatives. So let's just come up with a quick example that I want to share with you of why we might want to think about the second derivative. So I don't know, maybe 10, 15 years ago, there's a big oil spill, BP oil spill, right, down in the ocean. And when that happened, there was a hole in the side of the boat and the oil was leaking out. So the rate at which the oil was leaking out of the boat was the first derivative, right? But then the hole, because of the pressure from the oil, started getting bigger and bigger, right? So the rate at which the oil was coming out was getting larger and larger. And so the rate at which the rate was increasing was the second derivative. And that was important because knowing both the first derivative, the rate that the oil was coming out, as well as the second derivative, how quickly the rate was increasing, allowed sort of environmentalists and people dealing with the situation to have a better understanding of how long it would take until the entire boat was empty, sort of the timeline of what they were working against to try to, minimize the environmental impact. So that's just one example of a second derivative where that calculation was really important in that context. So let's talk about notation for a second. So again, because we had two parallel developments of calculus, we have two sets of notation. The Newtonian notation for a second derivative is going to look like this. Excuse me. So with the first derivative, we have one of these tick marks up here, these apostrophes. With the second derivative, we had two. If you were going to do a third derivative, you'd put 3, so on and so forth. So that's the Newtonian notation. There's two little marks here. And then if we're talking about the Leibniz notation, we actually have the number 2, but it looks like this. D squared y over dx squared. And so this is the Leibniz notation for the second derivative. So if you see either of these notations, right, we're talking about the second derivative, but you will notice that we tend to use the Newtonian notation a lot more, okay? So that's what the notation is going to look like. And now we need to think about how we can construct our understanding of the second derivative. So I want you to remember from when you were learning about constructing the first derivative as a function, these three really important rules, okay? So the relationship between the original and the first derivative is that if the original function is increasing on some interval, so it's going up from left to right, that means that the first derivative is going to be positive on that interval. So remember, if you draw in a bunch of tangent lines, you will see that they are all positively sloped. So we know that the derivative is positive whenever the original function is increasing. Secondly, if the original function is decreasing on an interval, then the derivative is negative on that interval, right? So if the original function is going down from left to right, we know the slopes of the tangent lines will be negatively sloped, so we know the derivative will be negative. And then finally, if the function is constant on an interval, then we know that the derivative is 0. And when we talk about constant, there's sort of two ways we think about it. So constant can be like a horizontal line is constant, but also the point where your function changes from increasing to decreasing, we consider that point where it changes to be constant as well, okay? So we're going to start by just remembering those rules, okay? And what we'd like to do is we're going to start with this function here. So one of the sort of things I'm going to mention here that's going to become really important sort of for the rest of our course is that whenever we're doing graphical analysis, it's going to be incredibly important to know which graph you are looking at. Are you looking at f of x? Are you looking at f prime of x? Or are you looking at f double prime of x, right? Because that's going to give you different information. So we're going to do two things here. So you'll see the graph is repeated here. And so the two things we want to do. First, we want to figure out on what intervals is the first derivative of this function positive, negative, and 0. So we are trying to relate what the original function, which is graphed here, is doing, so increasing, decreasing, to help us determine where the first derivative is positive, where the first derivative is negative, and where the first derivative is 0. So these are counting by ones, and then same thing over here, -1, -2, -3, etc. So I want you to look at this and sort of figure out where those intervals are, that the first derivative will be positive, negative, and 0. And then after you've done that, we're going to take it a second step and we're going to try to graph the first derivative based on the original function. So it's going to be helpful to have this information first, which is why we're going to find those intervals. And then we're going to use that to try to help us graph the first derivative. So this goes back to 2.2, which is what we looked at last week. So hopefully you have some notes or you kind of remember how that worked, but try your best to see what you can do. I'm going to give you 3 minutes and then we're going to go through this together. So again, this is not new. This is going from the original to the first derivative. We're going to practice that and then we're going to sort of tie in the second derivative after this. So take 3 minutes, try it out. If you have questions, the TAs can help. If there's someone near you, feel free to chat with them and then we'll go through it together. Okay, take about 30 more seconds. Okay, so our first step is we want to look at the original function, f of x, and determine where the first derivative is positive, negative, and 0. So I recommend doing the zeros first. I find that the easiest. You definitely don't have to do it that way, but when I do it, I find that when I find the zeros first, it helps me split up the intervals. So the first derivative is going to be 0 whenever we have a horizontal tangent line, right? So we're going to have one here at 0 and another one here at 4. So the slopes of those lines are going to be 0. So the first derivative is going to equal 0 at x equals 0 and at x equals 4. Okay, so 2 places. And so again, the reason I mentioned doing that first is that helps split up the intervals now for the other 2 parts. So our first derivative is going to be positive when the original function is increasing. Okay, so we see that we are increasing in the first part of this function until we get to 0. Okay, so there's sort of 2 ways you can write this. You can use the literal -3 to 0, or if you assumed it went on forever, you can use infinities. Either is fine since I didn't give you instructions about whether or not this was the whole graph. And so here, let's call this negative infinity to 0. So starting way over here at negative infinity, all the way until we get to 0. But we're not going to include 0 because 0 was constant. So we use the open brackets. Okay. And then also, there's this teeny tiny part over here where we start increasing again after 4. So we can say 4 to positive infinity. We are increasing again, assuming it goes on forever. And again, the alternative, you could have done something like -3 to 0 and 4 to 5, which is just what we see on the graph. And again, since I didn't specify whether or not this was the entire graph or if it went on forever, either of these are fine for now. So the idea is that we're looking for where it's increasing to tell us where the first derivative is positive. We can do something similar for where the first derivative is negative. By looking at where our function is decreasing. Okay, so we're going to be going down from left to right between 0 and 4. Okay, so again, I'm using interval notation. The derivative is going to be negative from 0 to 4 because that is where the function is decreasing. Okay, so now I know where I'm going to be positive, negative, and 0. Okay, and again, I'm basing that on where the original function is increasing and decreasing. So now I want to use that to try to draw the first derivative, right? So this is the same function as before, but now I want to use this information to draw the first derivative. So I'm going to start by drawing in my zeros. I said the first derivative will be 0 at 0 and 4. So on my new graph at 0 and 4, it's the same scale as the other graph. Okay, I know that the first derivative is going to equal 0. I'm going to just check these off so you can see where these values are. -1, -2, -3, -4. Okay, so now we also know that the first derivative should be positive, right, from negative infinity to 0. So in this space here, what does it mean for the derivative to be positive? it means it's got to be up here above the x-axis, right? So somewhere up above the x-axis. Same thing for after 4. We should be positive, so we should be somewhere up here. Between 1 and 4, or between 0 and 4, excuse me, that's where the first derivative was negative. And if the derivative is negative, negative means we are below the x-axis. So we're going to be down here between 0 and 4. So the shape of our graph is that we start up here, we have to go through this 0, then we're down here, then we have to go through this 0, and we're back up here, okay? If we wanted to be precise, we could calculate some tangent line slopes and plot them. And what we would get is this sort of U shape. We talked about the U shape in 2.2. It's going to look something like this, okay? So the first derivative is going to look like this. So the original function had this shape, and then we plotted the slope of every single tangent line, and we got the first derivative function, which looks like this. Okay, so that's how we're applying our rules here to try to understand what we can learn from the original function going to the first derivative. Now, what we're going to do today is we're going to say, okay, well, what if we have the first derivative? How can we use that to talk about the second derivative? And the good news is the process is going to be the same. So what we're going to be doing is we're going to take the first derivative and do the same type of thing. We're going to ask, you know, where is it increasing and decreasing? Where is it 0? And we're going to be able to use that to then talk about the second derivative. Okay. So I replotted the first derivative here. And what we're going to do is the same thing we did before. So we're going to determine the intervals where this function, right, is increasing and decreasing to tell us where the derivative of this function will be positive, negative, and 0. Okay, so this function is the first derivative, but when we do the same thing that we did before in determining where it's increasing and decreasing to figure out where its derivative is positive, negative, and 0, is going from the first derivative to the second derivative. Okay, so again, I want you to look at this picture and determine where the derivative of this function will be positive, negative, and 0. And then we're going to try to graph the derivative of this function. Okay, so those are the 2 steps here. So again, I'm going to give you 3 minutes. You can look back at your notes for the last example so you can see what we did if you have any, you know, concerns about that. And then in 3 minutes, we'll go through that together. Okay, take about 30 more seconds. All right, so again, I'm going to start with where the derivative of this function equals 0, because that helps me break things up into intervals. So I notice here that I do have a horizontal tangent line right here at x equals 2. So that's the place where if I draw on a tangent line, I see it's going to be horizontal. It's not a coincidence that these tend to happen at the tops of hills or the bottoms of cups. So just keep that in mind, for future work we do. So we have this horizontal tangent line at x equals 2. So then again, we want to consider where we're increasing and where we're decreasing. So we're going to have the derivative of this function is going to be positive whenever we are increasing. So notice that after 2 is where this function is going up, right? So with interval notation, we can say from 2 to infinity. We are increasing, and therefore the derivative will be positive. And then the derivative will be negative whenever this function is decreasing, which is happening to the left of 2. Okay, so we're decreasing. And so that's going to happen from negative infinity to 2. Okay. So we're treating this function like an original function, right? But we know from before that this is the derivative of something else. So we're going to kind of try to link that all together in a few minutes. But keep in mind, we're treating this like an original function and then trying to talk about the derivative of this function right now in this context. So when we try to graph this, again, we're going to start by graphing the zeros. So we know that there's going to be a 0 when x equals 2. So we plot that right on this derivative picture. And then we see that before 2, right, from negative infinity to 2, we should be negative. So we're going to be down here. And then after 2, right, that's where we are positive based on the work we did above. So we have a function that starts down here, goes through our 0, and ends up here, okay? And so we know from the earlier section that when we have this U shape, we end up with something that's fairly linear. So when we start with a picture that looks like this, and we do analysis on what the derivative would look like, we end up with something that looks like this as the derivative, okay? But now, what did we do, right? So this function that we started with was already a derivative, which means that this function we produced is a second derivative, okay? So if this is f prime of x, this is f double prime of x, okay? But the analysis works the same whether you're going from the original to the first derivative to the second derivative to third derivative. I could give you the picture of a 50th derivative and ask you to draw the 51st derivative, and it would be the same idea. We'd look at where it's increasing and decreasing to determine where it's positive and negative. And so since this process is the same to go from one function to the next derivative, we extend the rules that we had learned before to now say, since the second derivative is the derivative of the first derivative, it follows that if the first derivative is increasing on an interval, then the second derivative is positive on that interval. So this is the same statement we had before, only now we're talking about going from the first derivative to the second derivative, okay? If the first derivative is decreasing on an interval, then the second derivative is negative. And if the first derivative is constant, then the second derivative is 0 based on that interval. Okay, so the main point right now is if you were to take the next derivative of any function, whether it's original to first, first to second, second to third, third to fourth, we're going to be doing it the same way by looking at where the function is increasing and decreasing, right, and 0, and then figuring out what that means for the next derivative, which will be positive, negative, 0, and then we're able to graph it using the same rules as before. So that means we have a process to always be able to talk about the next derivative. So we have the original to the first derivative. That's the first thing we did, right? That was here, original to first derivative. We have the first derivative to the second derivative. But what we don't have is a relationship yet between the original function and the second derivative. That's like the missing link here. So this is a picture, okay? This is the original function, and this is the second derivative. And what we want to be able to do is think about if there exists some sort of relationship between these two functions. We know that the first derivative is related to the original and the second derivative, but what about the original and the second derivative? So what I'd like you to do is I'd like you to think about this for a minute, and I want you to think about the types of ways we describe graphs to see if there's any relationship here, okay? So I just want you to take a minute, jot down any ideas that you have, and then we'll kind of go through and think about how that might work. Okay, so the properties that we look at on a graph, we have positive, negative, increasing, decreasing, concave up, concave down, okay? If you look at the original function and you think about positive, negative, right? You'll see that this is negative, but it's 0 at 0. So that means if it was related to where the original function was positive or negative, we would expect the second derivative to have some property that was different at 0, but the same everywhere else. But we see that there's nothing different specifically about what's happening at 0. So I think we're gonna eliminate that one for now. If we think about increasing, decreasing, we are increasing until 0, decreasing from 0 to 4, and then increasing at 4. So we would expect something to happen at 0 and 4, because that's where we change from increasing to decreasing. And I don't see any obvious link there. So then when we think about the last property, which is the concavity, we see that we're concave down until 2, and then concave up after 2. So we would expect something to happen at 2 on the second derivative if we were linked to concavity. And what you may notice here is that at 2, we go through a 0, which is interesting. But also that when we are beyond 2, the second derivative is positive. But when we are before 2, the second derivative is negative. And that is directly related to the concavity of the original function. Okay, so this is concave down until 2, and then it's concave up after 2. So the relationship between the original function and the second derivative has to do with the concavity of the original function being linked to the sign of the second derivative, okay? And so right here at 2, this point where the second derivative is 0, and this point where we change concavity, this is called an inflection point. Can't remember if we talked about this before, but the inflection point is where we change concavity, okay? And notice that that inflection point maps directly to where the second derivative equals 0. So now we have a robust set of relationships between the three functions that we want to look at: the original function, the first derivative, and the second derivative. And so there's a summary here of all these relationships, where if the original function is increasing, the first derivative is positive. So those relationships that we started with. Then if the first derivative is increasing, the second derivative is positive, right? So this is a relationship between the first derivative and the second derivative. And now the third set says if f of x is concave up on an interval, then the second derivative is positive on that interval. If f of x is concave down, the second derivative is negative on that interval. And if f of x is at an inflection point, then the second derivative equals 0. Okay, so these are our sets of relationships that are going to be important for all of our graphical analysis going forward. So I strongly recommend that you have these handy somewhere at most times. And so what you're going to want to do with these is you're going to be given some sort of graph, either an original, a first derivative, or a second derivative. Once you know which graph you have, you want to look at what we are asking you to do. So if we give you a graph of a second derivative and ask you to tell me about the first derivative, then we're going to use these, and we're going to look at where the second derivative is positive, negative, or 0, and that will tell me where the first derivative is increasing, decreasing, or constant. If I give you a second derivative graph and ask about the original function, that relationship is the third set of rules. If I give you a first derivative graph and ask you about the original function, that's the relationship in these first set of rules. So having these handy is going to help you whenever you have a graph that you have to analyze. Okay, so now that we have all these relationships, we want to make sure that we are comfortable identifying the different things that they are telling us about any particular graph. So we're going to do an exercise that will hopefully help tie these rules together. And so here we have a function, and this function is f of x. So this is an original function, okay? And what we want to do is we want to use this function to determine if each of these things is positive, negative, or 0, okay? So we're counting by ones here. So 1, 2, 3, 4, -1, -2, -3, -4, okay? And so what we're looking at is f of -2, so the function evaluated at -2, is that positive, negative, or 0? The derivative evaluated at -2, and then the second derivative evaluated at -2. So this is a functional value. Here we're considering the slope of the tangent line by looking at whether the function was increasing or decreasing. And then for the third part, we're looking at the concavity now that we've added that rule. And so we're going to do that at 3 points. We're going to do that all for -2. We're also going to do it for 0. Look at the function, the derivative, and the second derivative. And then also at 2.5. Okay, so I'm going to mark these on the graph so you can see exactly where they are. So -2 is here. 0 is here. And 2.5 is about right here. Okay. So I want you to think about whether each of these things is positive, negative, or 0. So maybe 2 minutes, try it out, just mark down a plus, minus, or 0 for each one, and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's start with what's happening at -2. So that's this point here. First, we're trying to determine if the functional value is positive, negative, or 0. So when we look at the functional value, we really want to know, are we above or below the x-axis? So you'll see here that the y value is going to be negative because we are below the x-axis. So the functional value is negative. Now we want to consider the derivative. So the derivative, we can either sketch in a tangent line or look at whether the function is increasing, decreasing, or 0. So I notice here that my function is decreasing. And if I were to draw on a tangent line, that would have a negative slope. So f prime of 2 is also negative. Now to talk about the second derivative, this is new, this is sort of our new property here. We want to consider the concavity. And so I want to sort of sketch in the whole picture of what we're looking at, right? We're looking at a point that's right here in this U. So this whole shape right here is concave up. So this particular point is in a portion that is concave up. If your graph is concave up on the original, that tells you that the second derivative will be positive, okay? So now let's do something similar to see what's happening at 0. So f of 0 is the functional value. I see that it is above the x-axis. So that means the functional value is positive. If I consider the slope of the tangent line, I notice I'm going to have a horizontal tangent line. I'm sitting right at the top of a hill. So the derivative here will be 0. And then for the second derivative, I notice that this area is concave down, right? It's downward sloping all right here. Since 0 is part of that whole downward shape, that means that the second derivative is going to be negative because that is concave down. And then finally, at 2.5, I have this part right here. So depending on your graph, if you print it out, it looks pretty close to 0, but the way I drew it, it's positive. So I'm going to say this is positive. If you have this printed and it looks closer to 0 for you, 0 would also be okay. It's just the way I marked it. For the derivative, I see that I'm increasing right here. I'm going up from left to right, which means my derivative will be positive. And then for the concavity, I notice that this is the point where if I look to the right of it, I'm concave down. But if I look to the left, I'm concave up. So that says to me that this is an inflection point, which means that at 2.5, the second derivative is going to be 0. Okay, so one of the main things I want you to notice here is that just because one thing is positive or negative doesn't mean the derivative or second derivative needs to be positive or negative. We're evaluating different things on the graphs to determine these signs. Okay, so if the functional value is negative, the derivative could be positive or negative or 0. What we have to look at is the slope of the tangent line. Same thing for the second derivative. You have to look at the concavity. We are evaluating 3 different graphical properties to figure out the sign. Okay, so let's look at one more example here that will hopefully help us link everything up. So given the tables below, determine the intervals where f of x, so the original function, is most likely concave up and concave down. So we've talked about concavity before when we have an original function, because we talked about approximating the first derivative and then using that to determine concavity. We started with average rates of change, then we moved on to the instantaneous rate of change, but we've done this on a table a few times. So the first table, we're going to be approximating the instantaneous rate of change for every point. But for the second table, I want you to notice that this table gives you values of the first derivative. So you need to think about how you would use that to figure out where the original function might be concave up or concave down. And so this is where you might want to reference back those sort of rules of how things are linked up. So I'm going to give you about 3 minutes to try to figure out for both of these, again, 2 different tables, so you do them separately, where we think the original function's concave up and concave down, okay? Let's take a couple minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay, so as a reminder, if we go back to our rules here for a second, we're trying to determine the concavity of the original function. And so the only place we talk about concavity is this third set of rules, okay? So we can talk about concavity if we know the sign of the second derivative, okay? Well, the information we have is not about the second derivative yet. So how can we figure out the sign of the second derivative? Well, the sign of the second derivative is determined in this second set of rules. So where the first derivative is increasing, the second derivative is positive. Well, that's great because if we know the second derivative is positive, we know the original is concave up. So we are linking these 2 sets of rules. So what we want to do is determine some information about the first derivative to help us understand the sign of the second derivative, which will then get us to the concavity. So as I mentioned, we want to go through the first derivative. So we have to approximate the first derivative on this table. So we've done this before. So for an endpoint, we're going to do the change in y over change in x using the point next to it. So 3 minus 1 is 2 divided by 1 is going to give me 2. For middle points, we're going to do the 2 points around it. right? So 6 minus 1 is 5, divided by 3 minus 1. So 5 divided by 2, we get 2.5. Here we do 10 minus 3 is 7. 7 divided by 2 is 3.5. Then we're going to do 13 minus 6, which is 7 divided by 2 is 3.5. Then we're going to do 15 minus 10, which is 5 divided by 2 is 2.5. And then 16 minus 13 is 3 divided by 2 is 1.5. And then again, on the end point, you're just using the one next to it. So 1 divided by 1 is 1. So now we have an approximation of the first derivative. And so now that we know something about the first derivative, we go to the rules that link the first derivative increasing or decreasing with where the second derivative is positive or negative. Okay, so the first derivative appears to be increasing at the beginning. So we have 2, 2.5, 3.5. Those numbers are going up. Okay, so here, this is increasing. If your first derivative is increasing, your second derivative is positive. Okay, that's the relationship there. And then where are we decreasing? Well, let's see. So 3.5 to 3.5, that's not decreasing, that's constant. So 3.5, 2.5, 1.5, 1, those are decreasing, which means that is where the second derivative is negative. And then right in this little spot here, 3.5 to 3.5, right? That's where we're constant. I'm going to put CON. So that is where we're going to predict that the second derivative is 0. Okay, so that's where we're turning around. So I used where the first derivative was increasing or decreasing to figure out the sign of the second derivative. Now that I know that, I go back to my rules and I go to my third set of rules, because if I know the sign of the second derivative, the sign is positive, that tells me the concavity of the original function. So when the second derivative is positive, the original is concave up. Okay, so we said the second derivative was positive here, which means that on that interval, the original function is concave up. Similarly, when the second derivative is negative, on that same interval is where we are concave down. And then right here in the middle, this is the most likely place that we will have our inflection point. Okay, so when we do this type of work and we want to come up with a final answer, we're going to talk about the concavity in terms of the x values. So this is going to be concave up from x equals 1 to x equals 3. Okay, we're going to be concave down from x equals 4 to x equals 7. And we are most likely to have an inflection point between 3 and 4. So we'll actually use between x equals 3 and x equals 4. You can say it's on the interval 3 to 4, but usually the way Wiley asks for this is it's most likely between which two values, 3 and 4. Okay, so there's a lot of work that goes into figuring out how all these pieces fit together, and that's the work that we're doing in this section. We're going to do something similar on the second table, only we can cut out a step because we are given the derivative. So we don't need to calculate the derivative. Instead, we're going to take these values and look at where they are increasing and decreasing. So 2, 5, 6, 12, 17, those are all increasing. Okay, and again, since this is the derivative, whenever the derivative is increasing, that tells me that the second derivative is positive. If the second derivative is positive, the original function is concave up. And again, I'm going to look at the x values from 1 to 5. Okay, and then Notice here that there's nowhere that's constant like we had here. Instead, we have 17, 14, 11. So we are decreasing here. If your first derivative is decreasing, your second derivative is negative. If your second derivative is negative, the original function is concave down. And we expect it to be concave down from 5 to 7. Now notice that 5 shows up in both intervals, but I'm using open interval notation. So 5 is not included in either interval. And what that tells me is that 5 is the most likely place where I might have an inflection point, because that is where I changed from positive to negative. Okay, so again, the analysis from this point on is the same as the analysis once we had gotten the first derivative, but in the first step, in the first table, we had to actually find those values. Okay, this takes a bit of work and practice. So if it feels like a lot right now, you will get more used to it as we go, I promise. Okay, so that's second derivatives and how they relate. Now we're going to switch gears and talk a little bit about marginal analysis. And so this is sort of linked and building onto what we talked about in 1.4. So we actually talked about marginal analysis a little bit in 1.4, and we did it a little bit early to link up here. So you may need to go back to those notes if you don't remember when we were talking about cost and revenue. But we talked about marginal analysis when the functions were linear, okay? And we said, okay, the rate of change of a linear function is the slope of the line, and that's sort of what we were working from, right? So we were assuming all our functions were linear, and now we're going to take it a step further now that we've worked with some nonlinear functions to talk about marginal analysis in general so that our functions don't have to be linear. So marginal cost. So let's talk about what marginal cost is sort of as a definition and then how we calculate it. So marginal cost, which we're going to notate as C prime of Q, so the derivative of cost, is the additional cost to make one more item. Remember, cost is how much it costs you to make something, okay? So the marginal cost is the derivative, the rate of change of cost at a point, and it's the cost to make one more item. Now, one of the things that we're going to notice here for all our marginal analysis is that we're going to be using right-hand estimates. Oops, right? So when we were estimating derivatives on a generic function, we would do the left and the right and average them together. When we are talking about business, we are always doing the right-hand estimate. And the reason why is because we're always talking about what happens to make or sell one more, which means we're going to the next one in business to decide if we should do the next one. So if it doesn't tell you to do a best estimate or a left-hand estimate, the default for business examples are right-hand estimates, okay? Now for the revenue, just like the marginal cost, the marginal revenue is the additional revenue from selling one more item. Okay, and so when it was linear, we knew that this was the slope, right? That price. If we're selling blankets for $10 each, if we sell one more, we make another $10, right? But that's not going to be true if our revenue function is not linear. So that's why we have to define it a little more generally. And then the marginal profit, which we're going to write as pi prime of Q, is the additional profit from making and selling one more item. Okay, so again, if you know the marginal revenue and the marginal cost, we can subtract marginal revenue minus marginal cost, and that will give us marginal profit. And like I said, we worked on this with linear functions, so it should be somewhat familiar. So if the cost of a function, if the cost function for representing an item is linear, right, then the marginal cost is just the slope of the line. And that's what we did back in 1.4. We looked at linear functions. But if the cost is not linear, right, then the marginal cost is the slope of the tangent line at, and we're going to call it Q star just to mean for some particular quantity. Okay, so you'll see a cost function here that's linear, right? If you pick a Q star, so any point, right, the marginal cost is going to be the slope of the line because all the tangent lines are going to lie on the line. But when you have something that's not linear, right, we have to approximate that slope just like we have been for other types of functions, right, is the idea. So if your function is linear, whether it's cost, revenue, or profit, then the marginal cost, revenue, profit is just the slope of the line. If it's nonlinear, that's when we're going to bring in all these methods that we've been trying to talk about nonlinear functions in chapter 2. So let's look at some examples. Okay. So example 1, suppose that the revenue for a certain item is given in the table below. Determine the marginal revenue at Q equals 15. So here we're trying to approximate R prime of 15 from a table. We've practiced looking at rates of change on a table, but I want to remind you that when we do this with revenue, we're always looking to a right-hand estimate. Okay, I'm also going to have you try example 2. So suppose the cost of a particular item is given in the graph below. So we have this cost function. You can see it's linear. We want to approximate the marginal cost at Q equals 10. And then for part B, if R prime of 10 equals 15, so this pairs with part A, then what is the marginal profit for this item? So you have to do part A before you can do part B. Part B gives you some additional information so that you can solve the problem. So what I would like you to do is both of these examples, so practicing on a table and on a graph. I'll give you 3 minutes, try it out, and then we'll go through these 2 examples together. Okay, take about 30 more seconds. All right, so we have this table and we're trying to approximate the marginal revenue at 15. So we can see that 15 is here. If this was not an economics problem, if this was just f of x, we would use the 2 points around it and do change in y over change in x. But when we talk about business examples, we are always looking ahead to the future. So we do a right-hand estimate, which means we're going to use the point to the right of 15 to do our approximation. So now the change in y will be 180 minus 160 over 20 minus 15. So that's going to give me 20 over 5, which gives me an approximation. R prime of 15 equals 4. And so what does that mean? That means that if I were to sell one more item, I would expect to increase my revenue by $4. Okay, so I'm going to be making $4 per item when we are at a level of selling 15. Okay, so again, it's a little bit different because we're only doing a right-hand estimate in economics, but otherwise the process is the same as what we've been working through with other types of problems. Okay, for example 2, suppose the cost of a particular item is given in the graph below. Approximate the marginal cost at Q equals 10. So I can come up here and think about where this point is, but what I notice is that the cost function is linear. Since it's linear, then I know that the marginal cost, C prime of 10, is going to be the slope of the line. So I need to figure out a good way to determine the slope of the line. So what I'm going to do is I'm going to pick 2 points on the line that feel easy to work with. Hopefully that's what you figured out. If you didn't pick the same points as me, that's okay. You should still get the same thing that I get here. So I'm going to pick the point at 10. So 10, comma, I'm going to call that 150 because it looks like it's halfway between 100 and 200. And then I'm going to pick the point 30, comma, 300. That looks like a easy point for me to work with. But again, you can pick any 2 points on this line. If you didn't pick the same 2 points as me, you should still get something similar. So now the slope, change in y over change in x. So 300 minus 150, change in y, over 30 minus 10. So that's 150 over 20. And if I crunch that, I get 7.5. So that means C prime of 10 is $7.50 per item. So remember, money, right, has 2 decimal places. So when I'm making 10 units of whatever it is I'm selling, it's going to cost me an additional $7.50 to make another item. Okay, that's what this is telling me. So now for part B, I'm also told that R prime of 10 is 15. So that's $15. So what is the marginal profit? So the marginal profit at a threshold of 10 items is going to be the marginal revenue minus the marginal cost. So how much additional money do I get from selling the 10th item minus the additional cost it costs me to make the 10th item, right? So R of 10 or R prime of 10 is 15 minus C prime of 10 is 750. So that means my marginal profit is $7.50. So if I make and sell an additional item, so going from 10 to 11, I expect to get $7.50 in additional profit. Okay, so 2 quick things here I just want to point out. Again, we're using right-hand estimates when appropriate, right? When it's linear, left and right are going to be the same. But also when we talk about what's happening, we're talking about going to the next one, right? So this is going from item 15 to item 16, would, bring me in an additional $4. This is going from item 10 to item 11, right? So we're always talking about the cost to do one more. Okay, so let's take a look at this example. This is one that has a lot of information that sometimes gets a little bit lost in the shuffle. So there's a lot of good things that can come out of this. So consider the graph below and determine where this product is making a profit. So this first part where it's making a profit, we can work out without too much trouble, but there's a lot of sort of things happening behind the scenes that I want to talk about as well. So if you look at what's going on here, right? If we're going to talk about where we're making a profit, we're really looking for where revenue is greater than cost, okay? We're looking for where the amount of money that we take in is more than the amount of money we're spending, right? And so that happens, in this interval here, where the red line is above the blue line, because R is revenue, C is cost. So we can see that that's happening from 130 to 215, that we're going to have a profit. Q equals 130 to Q equals 115. Revenue is greater than cost. So we have profit greater than 0. Okay. But within this profit little range here, there are times when it makes sense to produce more and times where it does not make sense to produce more. And so the way we sort of think about this is we want to be at the place in this little interval where the cost and revenue are the farthest apart, because that's where we get the most profit. So that's roughly here. Okay, so whatever that number is, that is where we're going to get the maximum profit. Which means that if we are to the left of this max profit, we do want to make more because we want to get to this level, right? And what's happening to the left here is that my marginal revenue, which is this sloped line, is greater than my marginal cost, right? The slope of the revenue line is steeper than the slope of the cost line. So marginal revenue, marginal cost, and in this area, marginal revenue is greater than marginal cost. So make more. We want to make and sell more because we want to get to this particular line. When we are past that line, what I want you to notice is that when you compare the slopes of marginal revenue and marginal cost, now marginal cost is greater than marginal revenue. And so our profit is actually less because that gap between the two is smaller. So in this area, marginal cost is greater than marginal revenue. So we do not make more. Okay, so what are we emphasizing here? That this whole area, we make a profit, we make money. But we are greedy business people and we want to make the most money. So even though we're making money over here, right, we're making less money than if we were here. So we don't want to produce more because we're making less and less of a profit, right? We want to be here. So when you're looking at a picture like this, first you want to figure out where is the profit. Then once you have that little sort of interval, we want to consider when we want to make more and when we do not want to make more. And again, what we can look at is if the slope of marginal revenue is greater than the slope of marginal cost, that means that these are getting further and further apart and we want to make more. But if marginal cost is greater than marginal revenue, we are not going to make more because marginal profit here will be negative. Okay, so it's a little more nuanced than just sort of where are we making a profit, because within that, there are better places to be in that sort of profit interval. okay? And so for the last example here, we won't have time to sort of do the whole thing, but we can do part A and then you can do part B at home. So let's see if Q represents the total cost of producing Q items. Suppose C of 15 equals 2,600, C prime of 15 equals 109. Use that to estimate the total cost to produce the total number of items. So we have information about the function. We have information about the derivative. That means that we are doing local linear approximation or local linearity. We talked about this last week. So we want to approximate C of 20. So that's what we want to try to predict, right? So we're going to use the information we have about the function at a point and the derivative at that point, C of 15 and C prime of 15. And then we have to multiply the derivative by how far away we are looking. So that is the point we want, 20, minus the point that we have, right? So now we need to plug in all these values. So C of 15, 2,600, C prime of 15, 109. And I think I said this before, but just to emphasize, the order here is really important. So it's always the new minus the old, because that's going to help us which direction we're going. So make sure you don't switch those. So we're going to do 5 times 109. You have to do the multiplication before you add them together. Order of operations. So 109 times 5 is 545. And then we add that to the 2,600. And we're going to get 3,145. Okay, so you can try the other one at home with 10. You'll have C of 10 equals C of 15 plus C prime of 15, and then 10 minus 15. So that'll be a negative calculation. But this one is local linearity. Okay, so try out the homework, do the quiz. I sort of recommend that you go to Drop-In Help this week to get answers to any of the chapter 2 mini quizzes you may have gotten wrong before the chapter quiz on Friday. Okay, have a great rest of your day, and I'll see you guys all on Thursday.